So now talk about the test procedure. First of all, let's run the machine. We're going to install our sample. I'm going to start with the gray one here. Fix it, make sure it does not move. So what we need to do, first we need to say that we are going to run the test. Number 1 test. How much is the thickness? We measured the thickness before. It is 0.5 for the thickness, and everything is good. We need to release the pendulum. So as soon as we release the pendulum, it's going to break our sample. As you can see here, the break is complete. It was like this. So there is no resistance. As you can see from the break, you will understand from the texture that no resistance happened here because this material is very brittle and it's break very fast, very easy. So the machine asks us what type of break we have here. We have partial, hinge, or complete. As you can see here, we have a complete break. So we're gonna enter 1 complete. So this is our absorbed energy. Write down this absorbed energy. Our breaking energy is 7.69 inch-pound force for the brittle material, and S1 is breaking energy divided by width. If you remember, the width was 0.5, so 7.6 divided by 0.5 gonna give us 15.388. We are going to do the next sample. Again, install the sample. Hit enter. Coming back to the beginning. Again, we're going to run the test. 1 enter, 0.5 enter. Pendulum is ready, and we're going to release it. So, very interesting. This one is hinge. It's not completely break because it is a ductile material. And remember, I asked you guys to take a guess between ductile and brittle, which one going to be need more energy to break. So let's put that on hinge. Number 2, enter, and energy on that one is 2 times bigger than the previous one. It is 13.239. So, and that makes sense. Brittle material going to absorb more energy than ductile material going to absorb more energy than brittle material. Brittle material going to break very fast, like this. They don't have any resistance in front of the hammer, and so they break fast. And you can see 2 parts. But ductile one, it's going to take more energy. Later on, when we are talking about stress-strain diagram, you will see that why ductile material needs more energy, because their elastic region is much bigger than elastic region on brittle material. So for elastic region here, going to be longer to create the break. Break happen after plastic region. So for both of them, we have first elastic, then plastic, then breaking. For the brittle material, elastic is very simple, plastic are much bigger, and then breaking. All happen very fast, even you couldn't see any deformation on the texture. Texture is like breaking very fast. But for the ductile material, elastic, plastic, and break. Passing elastic is going to be probably longer than brittle material, but plastic region for those is very big, and this is why we have hinge. And then breaking. So they're going to absorb more energy to yield. And as you can see here, the energy is almost 2 times bigger than the previous one. So let's try the last one. I'm going to install that again here. Number 1, 0.5, same. It's ready. Release the pendulum. This was also is a complete break. Even this one is more brittle than the first one we had. And let's say complete. See the energy even much less than the first one, 1.7. So if I want to put them based on more brittle to more ductile, that's going to be like this. And if we want to write down the energy, this one was 1.7, this one was 7.5, and this one was 13.6 inch pound force. So this one was 7 times bigger than, and this one 2 times bigger than that. So this material is very brittle. This one is towards ductile, but it is still brittle, and this one is ductile. Thank you very much. This is all about lab number 1. We have a couple of calculations regarding to release energy and a couple of questions regarding to the observation that you guys had here during this lab procedure, and that I refer you to the lab handout 1, lab number 1, and you could answer those questions for this lab. Thank you very much.